Good day, and welcome to this in-depth lecture on refrigeration and air conditioning. In this first module, we will focus on refrigeration cycles, their underlying principles, and their applications. Our aim is to not only understand what these systems do, but how they achieve their cooling effect, why different designs exist, and where they are best applied. Refrigeration is essentially the process of removing heat from a space or substance and transferring that heat to another location, where it can be released into the environment. While the concept may seem simple, the engineering behind it involves thermodynamic cycles, component integration, and careful design choices. The science of refrigeration began in the 19th century with simple ice storage and mechanical cooling machines, and today it plays an indispensable role in industries such as food preservation, medical storage, manufacturing, and human comfort. Air conditioning, which we will examine later, is essentially an application of refrigeration, adapted for controlling air temperature, humidity, and cleanliness. 1. The reverse Carnot and Joule cycles. To understand modern refrigeration systems, we start with two fundamental thermodynamic models, the reverse Carnot cycle and the reverse Joule or Brayton cycle. 1.1 Reverse Carnot cycle. The Carnot cycle is a theoretical model that represents the most efficient possible cycle operating between two temperature limits. In refrigeration, we consider a reverse Carnot cycle, meaning that instead of producing work from heat flow, as in power plants, we consume work to move heat from a cold space to a warmer one. In this cycle, the refrigerant absorbs heat from a low-temperature source. A compressor raises the pressure and temperature of the refrigerant. The refrigerant releases heat to a high-temperature sink. Expansion returns the refrigerant to its initial pressure and temperature, ready to repeat the cycle. Although the reverse Carnot cycle is not practical for real systems due to the slow, reversible processes it requires, it serves as a benchmark for evaluating the efficiency of actual refrigeration systems. 1.2 Reverse Joule Brayton cycle. The reverse Joule cycle, or reverse Brayton cycle, is another theoretical cycle used mainly in air cycle refrigeration systems. Here, air itself acts as the working fluid without undergoing a phase change. This method is still used in some aircraft refrigeration systems, where simplicity, reliability, and lightweight construction are essential. In practice, both cycles help us understand the trade-offs between efficiency, size, weight, and operational simplicity. 2. Vapor compression refrigeration system. The vapor compression cycle is the most widely used refrigeration method worldwide. It forms the basis for domestic refrigerators, air conditioners, and many industrial systems. 2.1 Main components. Evaporator, where the refrigerant absorbs heat from the cooled space, evaporating from liquid to vapor. Compressor, raises the refrigerant vapor's pressure and temperature. Condenser, rejects heat to the surroundings, condensing vapor into liquid. Expansion device, it reduces the refrigerant's pressure and temperature before it enters the evaporator again. 2.2 Operation. In a vapor compression system, the refrigerant changes phase between liquid and vapor, allowing it to absorb and release large amounts of heat efficiently. This cycle dominates commercial and residential refrigeration due to its high efficiency, compactness, and adaptability to different temperature ranges. 3. Vapor absorption refrigeration system. The vapor absorption cycle differs from vapor compression in one major way. Instead of using a mechanical compressor, it uses a chemical absorption process to move the refrigerant. 3.1 Working principle. Here, a refrigerant such as ammonia is absorbed by a liquid like water, forming a strong solution. This solution is pumped to a higher pressure and then heated, releasing the refrigerant vapor. The vapor then passes through a condenser, expansion device, and evaporator, just as in a vapor compression system. 3.2 Advantages and applications. Can be powered by waste heat or solar energy, reducing electricity use. Fewer moving parts, leading to lower maintenance. Often used in industrial cooling where heat sources are readily available. However, they are generally less efficient than vapor compression systems and are more suited for applications where heat is cheap or where electricity is limited. 4. Coefficient of performance, COP. In refrigeration, efficiency is expressed as the coefficient of performance, or COP. It is defined as the ratio of useful cooling provided to the work or energy input required. While the reverse Carnot cycle gives us the maximum possible COP, real-world systems fall short due to losses in compressors, heat exchangers, and piping. Higher COP means greater efficiency, which translates to lower operating cost and reduced environmental impact. 5. Pressure enthalpy charts. Pressure enthalpy charts are graphical tools used by engineers to analyze refrigeration systems without performing complex calculations each time. They plot the refrigerant pressure against its enthalpy and allow quick visualization of the refrigerant state at each point in the cycle. These charts help identify superheating and subcooling levels, diagnose system faults, estimate performance under various load conditions. 6. Types of refrigerants. Refrigerants are the working fluids that absorb and release heat in the refrigeration cycle. Choosing the right refrigerant involves balancing thermodynamic performance, safety, and environmental factors. 6.1 Classification. Chlorofluorocarbons, CFCs, now mostly banned due to ozone depletion. Hydrochlorofluorocarbons, HCFCs, transitional replacements, still phased out in many countries. Hydrofluorocarbons, HFCs, common today, no ozone depletion but still contribute to global warming. Natural refrigerants, ammonia, carbon dioxide, hydrocarbons, often environmentally friendly but may have safety concerns. 6.2 Selection factors. Cooling capacity, operating pressure, chemical stability, toxicity and flammability, global warming potential, GWP, and ozone depletion potential, ODP. 7. Air cycle refrigeration. In air cycle refrigeration, air is compressed, cooled, and then expanded to provide refrigeration without phase change. This is common in aircraft systems, where avoiding refrigerant leaks is critical, and where the system can make use of already available compressed air from the engines. Advantages include: no need for chemical refrigerants, lightweight and simple design, ability to provide cooling and ventilation simultaneously. 8. Multiple effect and multi-stage compression. These terms refer to ways of improving efficiency in large refrigeration systems. 8.1 Multiple effect compression involves reusing energy from one stage of compression to assist in another, reducing total power consumption. 8.2 Multi-stage compression breaks the compression process into two or more stages with intercooling between them. This reduces the work required and improves COP. 9. Heat pumps. A heat pump is essentially a refrigeration system designed to move heat into a space rather than out of it. In winter, it extracts heat from outside air or ground and delivers it indoors. In summer, the cycle reverses, and it acts as an air conditioner. Advantages: high efficiency for both heating and cooling. Environmentally friendly when paired with renewable energy. Long-term energy savings despite higher initial cost.